In the silent darkness between galaxies, there exists a delicate balance, a quiet gravitational symphony holding together a family of worlds. We call it the local group, a cluster of over 100 galaxies, bound not by proximity, but by the invisible pull of gravity. Most who look to the stars know its two titans, the Milky Way, our home, and Andromeda, the approaching giant. But there is a third, smaller, quieter, and often overlooked. The Triangulum Galaxy, known to astronomers as M33, orbits on the edge of this cosmic family, a graceful spiral of light, modest in size but immense in meaning. It does not boast the grandeur of Andromeda, nor the complexity of the Milky Way. And yet, in its unassuming form, Triangulum holds answers to some of the most profound questions in astronomy. It is a bridge between scales, between the colossal and the diminutive, the ancient and the new, the visible and the unseen. If the Milky Way and Andromeda are the kings of the local group, then Triangulum is its quiet scholar, observing, recording, and preserving the lessons of the universe in its spiral arms. But the local group isn't made only of spirals. Surrounding these great galaxies are dozens of smaller companions, dwarf galaxies, the faint ghost-like remnants of a time when the universe was young. They drift like cosmic fossils, each one preserving the early chemistry of the cosmos. Together, they outnumber the giants 100 to 1. They are not bright enough to dominate the sky. Most can't even be seen without powerful telescopes. Yet their importance outweighs their size. For without them, the great galaxies might never have formed. Our universe was not built by titans, it was built by dwarfs. Tiny clumps of gas and dark matter that merged and collided over billions of years, giving rise to everything, from galaxies to stars to planets, and ultimately to life. To understand how the universe evolved, we must understand them, the smallest, faintest, and most enduring of all galaxies. And so this episode is not just about Triangulum. Though she will guide our path, it is about the forgotten neighbors of the local group, about the unseen scaffolding of cosmic structure and the fragile balance between isolation and interaction. It is about what happens when small things, united by gravity, create something vast beyond imagination. For centuries, Triangulum went unnoticed, while Andromeda dazzled the skies and the Milky Way inspired myth and poetry. Triangulum sat quietly in the background, a subtle smear of light in the constellation of the same name. It wasn't until the early 17th century that astronomers even recorded its presence. Later, in the 20th century, as telescopes reached beyond the veil of our own galaxy, we began to see its true form, a perfectly face-on spiral, delicate, open, and filled with regions of intense star formation. But what makes Triangulum fascinating isn't just its beauty, it's what it represents. It's the threshold galaxy, the line between the mighty spirals and the dwarfs that surround them. It's large enough to sustain complex structure, spiral arms, nebulae, clusters, yet small enough to show us what a galaxy looks like before gravity and time reshape it through mergers. Triangulum is, in many ways, what the Milky Way might have looked like billions of years ago. A young spiral still growing, still building its disk, still forming new stars at a steady pace. And in its simplicity lies clarity, a cleaner window into the mechanics of galaxy formation, free from the chaotic history of collisions that have scarred the giants. Yet to truly understand Triangulum, we must see it in context. Because galaxies, like stars, are rarely alone. Each one is part of a network, a cosmic ecosystem where gravity, motion, and time weave together countless destinies. Around Triangulum and its neighbors orbit dozens of smaller galaxies, each one a story in itself. Some are so small they barely deserve the title Galaxy, with only a few thousand stars. Others, like the Magellanic Clouds, are so bright they paint the southern sky. These are the dwarf galaxies, the overlooked architects of the universe. They formed first, long before spirals existed, when the cosmos was still a sea of hydrogen and dark matter. From their mergers, the great galaxies were born. And though most were absorbed long ago, a few survived, orbiting quietly around the giants that once consumed their kin. They are ancient beyond reckoning. Some of their stars were born less than 1 billion years after the Big Bang, older than the Milky Way itself. And their structures, fragile as they are, remain pristine, untouched records of the early universe. It is within these small, dim galaxies that astronomers have uncovered the fingerprints of cosmic evolution. Their chemical makeup tells us how the first stars forged the elements. Their orbits reveal the mass and shape of dark matter halos. Their numbers, or the lack of them, challenge our understanding of how galaxies grow. In many ways, the dwarfs are the universe's oldest diaries, scattered and incomplete, but invaluable to those who can read them. So as we journey through the local group, we will move from the luminous to the invisible. We will follow the graceful arms of Triangulum into the domain of the dwarfs, to galaxies so faint that they barely leave a mark upon the sky, yet whose existence holds the key to understanding all others. We will see how the Magellanic Clouds breathe life into the Milky Way, pulling streams of gas that ignite new generations of stars. We will trace the faint echoes of ancient systems like Draco and Fornax, survivors of a more violent cosmic age. And we will come to understand why, in the grand structure of the universe, smallness is not weakness. It is the foundation upon which everything else is built. Because the local group is not merely a collection of galaxies, it is a portrait of cosmic evolution frozen in time. It shows us how galaxies interact, grow, and sometimes consume one another. It reveals that even in a universe defined by scale, every system, no matter how faint, has a role to play. The giants may dominate the view, but the dwarfs define the structure. And within that balance lies the story of everything, from the birth of the first galaxies to the eventual fate of our own. So let us begin, not with the brightest or the largest, but with the quietest of the three. Let us journey to Triangulum, the modest spiral, the silent witness to the rise of the local group, and the gateway to understanding the smallest worlds that orbit within it. Triangulum, known to astronomers as M33, glides through the cosmos with a quiet elegance. In a universe dominated by luminous giants and sprawling spirals, it does not seek attention. It does not radiate like Andromeda, nor does it bear the intricate bulge of the Milky Way. And yet, for those who know where to look, Triangulum holds a subtle, mesmerizing beauty, a delicate spiral of stars, gas, and dust, unfolding in quiet rhythm, as if the galaxy itself breathes with the pulse of the universe. Its modest size belies its complexity. Even in seeming simplicity, there is a story of formation, persistence, and cosmic balance. From our vantage in the Milky Way, Triangulum lies roughly 3 million light-years away. Spanning approximately 60,000 light-years across, it is about 1/3 the size of our galaxy, with a mass of roughly 60 billion solar masses. Its scale is modest, but in this quiet simplicity lies a clarity that astronomers value. Triangulum's disk is nearly face-on, largely unobscured by a dense central bulge, and free from the scars of violent collisions that have shaped many larger spirals. Its open, flat disk allows a clear view of the spiral arms, where processes of star formation and galactic rotation can be studied in remarkable detail. The galaxy's spiral arms are a gentle, continuous dance of matter and motion. These arms are not simply patterns, they are dynamic engines of star formation, regions where gravity molds gas and dust into dense clouds that eventually collapse to form new stars. Among these, NGC 604 stands out as one of the largest star-forming regions in the local group, spanning over 1,500 light-years. Within this glowing nebula, tens of thousands of hot young stars emit intense ultraviolet radiation, energizing surrounding hydrogen clouds and sculpting luminous filaments. The interplay of radiation, stellar winds, and gravity produces a delicate structure, a cosmic lacework that extends across vast distances. Yet despite its immense energy, NGC 604 integrates seamlessly into Triangulum's arms, contributing to the galaxy's rhythm without overwhelming its serenity. Across the disk, smaller HII regions glow faintly, scattered along the spiral arms like luminous beads on delicate threads. Each represents a stellar nursery where new stars are born, live briefly in their intense youth, and contribute to the galaxy's chemical evolution. Massive stars formed in these regions synthesize heavier elements in their cores, releasing them into space through stellar winds and supernova explosions. These metals enrich the interstellar medium, ensuring that successive generations of stars, planets, and potentially life-bearing systems can emerge. Even in its modest scale, Triangulum participates fully in the ongoing alchemy of the cosmos. The galaxy's stellar populations reveal its layered history. Young, metal-rich population 1 stars trace the spiral arms, shining in blue-white hues and highlighting regions of recent formation. Meanwhile, older, metal-poor population 2 stars drift in the disk and halo, ancient witnesses to a past that predates the formation of the spiral arms themselves. This mixture of stellar generations indicates that Triangulum has maintained steady star formation over billions of years, punctuated by periods of enhanced activity, likely influenced by subtle interactions or accretion of gas. Unlike galaxies scarred by major collisions, Triangulum exhibits continuity, a measured evolution that allows its spiral arms to remain open and graceful. Its modest central region contrasts sharply with the dense bulges of Andromeda or the Milky Way. While some evidence suggests Triangulum may host a small central black hole, its mass is negligible compared to the supermassive black holes anchoring larger galaxies. The faint central concentration hints at a quiet evolutionary past, shaped less by mergers and more by gradual accretion and internal dynamics. In its simplicity, Triangulum offers a rare glimpse of spiral formation, largely unaltered by violent cosmic events, a window into processes often obscured in larger systems. Beyond the luminous disk lies Triangulum's diffuse stellar halo, a realm of ancient stars and globular clusters. These clusters, dense groupings of hundreds of thousands of stars, are remnants of the galaxy's early assembly, relics of smaller systems merged long ago, or survivors of early star formation. The halo stars trace the galaxy's formation history, their orbits shaped by gravity and past interactions. Some may have originated in other, now vanished dwarf galaxies, accreted into Triangulum over billions of years. By studying the halo, astronomers can map the galaxy's gravitational structure, the distribution of dark matter, and the evolutionary narrative of the local group itself. Triangulum's position within the local group adds further depth to its story. The galaxy is gravitationally bound to Andromeda, orbiting along a slow elliptical path. Subtle distortions in the outer disk suggest past encounters with its larger neighbor, where tidal forces may have tugged streams of gas and perturbed stellar orbits. Yet, unlike systems that are fully disrupted by such interactions, Triangulum maintains a coherent spiral structure, a quiet testament to its resilience. These interactions hint at the dynamic environment of the local group, where even galaxies that appear isolated are subtly influenced by their neighbors' gravitational pull. Triangulum also functions as a bridge between the giants and the dwarfs of the local group. While not as small or simple as the dwarf galaxies that populate the halo of the Milky Way and Andromeda, it shares characteristics with them: moderate mass, modest gravitational influence, and a history of gradual, largely undisturbed evolution. In this way, it provides insight into the continuum of galaxy sizes and behaviors, showing how modest spirals can maintain structure and function in a gravitationally complex environment. The chemical composition of Triangulum provides further insight into its evolution. Its spiral arms contain higher metallicity regions, enriched by repeated generations of star formation. The outer disk, in contrast, remains comparatively pristine, composed of gas that has undergone fewer cycles of stellar processing. This gradient reflects the measured pace of growth and the galaxy's long-term stability, and serves as a living record of star formation over billions of years. Each star, from luminous giants to faint dwarfs, carries information about the past, a fossil record embedded in starlight. Observational history shows the gradual unveiling of Triangulum's beauty. Early astronomers, including Al-Sufi in the 10th century, noted it only as a faint, nebulous patch. Charles Messier catalogued it as M33 in 1764. Yet even through telescopes of the era, the galaxy appeared as little more than a diffuse smudge. It was not until modern instruments, large ground-based telescopes, infrared and radio surveys, and the Hubble Space Telescope, that the intricate spiral arms, glowing nebulae, and faint halo became fully apparent. What once seemed a modest curiosity revealed itself as a richly detailed, dynamic system, providing a laboratory for understanding spiral galaxies in their quieter forms. The aesthetic experience of Triangulum is no less compelling than its scientific significance. Viewed from a distance, the spiral arms unwind like soft ribbons across the cosmic canvas, dotted with glowing clusters and diffuse nebulae. The halo stretches beyond the luminous disk, a faint whisper of stars marking the galaxy's ancient history. There is serenity here, a sense of balance and rhythm that contrasts with the dramatic chaos of merging giants. The galaxy appears alive, yet peaceful, participating in the grand processes of the universe without clamoring for attention. Triangulum's ongoing star formation, subtle interactions with Andromeda, and layered stellar populations combine to make it a galaxy of both quiet beauty and profound scientific value. It teaches us that significance is not always measured by size or luminosity. Even modest galaxies can illuminate the principles of formation, dynamics, and chemical evolution that govern the universe. Its structure, halo, and interactions provide insights into the continuum between dwarfs and giants, highlighting the interconnectedness of the local group. Ultimately, Triangulum embodies the balance between persistence and evolution. Its spiral arms rotate steadily, star-forming regions ignite and fade, and halo stars trace ancient orbits. It remains a constant presence in the local group, a witness to billions of years of cosmic change. In its quiet spiral glow, we perceive the rhythm of the universe, a pulse defined not by spectacle, but by patience, balance, and the enduring processes of creation. In contemplating Triangulum, we recognize that galaxies are more than the sum of their stars. They are living systems, shaped by gravity, enriched by stellar life cycles, and influenced by their environment. Even a modest spiral like Triangulum holds secrets of formation, dynamics, and cosmic evolution, offering a serene yet profound window into the mechanics of the universe. It is a galaxy that invites reflection, patience, and wonder, reminding us that the quiet, steady actors in the cosmos often reveal the deepest truths. In the vast expanse of the local group, Triangulum occupies a quiet, intermediary position. Neither a massive spiral nor a tiny dwarf, it drifts gracefully in the gravitational embrace of its more imposing neighbor, the Andromeda Galaxy. While Andromeda dominates the region with its immense mass and luminous presence, Triangulum maintains its own identity, orbiting at a distance of roughly 750,000 light-years from Andromeda's center. Their relationship is subtle, complex, and shaped over billions of years. A gentle gravitational conversation that has influenced both galaxies in ways we are only beginning to understand. Triangulum's orbit around Andromeda is not circular but elliptical, and though the timescale is vast, hundreds of millions of years for a single orbit, its effects are profound. Tidal forces from Andromeda exert a gentle pull on Triangulum's outer stars and gas, subtly stretching its disk and possibly triggering localized waves of star formation. These gravitational interactions are not violent. They are not catastrophic collisions, but rather soft nudges that shape the galaxy's structure over cosmic timescales. They reveal the delicate balance that allows a smaller spiral to coexist alongside a giant, maintaining form while still participating in the broader dynamics of the local group. Evidence of these interactions can be found in the faint streams of gas and stellar overdensities at the edges of Triangulum's disk. Though these features are subtle, they carry the fingerprints of Andromeda's influence, suggesting past encounters where gravity tugged at Triangulum's outskirts. In some regions, the spiral arms themselves may have responded to these encounters, compressing gas and igniting bursts of star formation. NGC 604, the galaxy's largest HII region, may in part owe its brilliance to these subtle gravitational nudges, a testament to how even modest interactions can shape cosmic evolution without destroying galactic integrity. The dynamics of this gravitational relationship also shed light on the distribution of dark matter within both galaxies. Triangulum's orbit, the motion of its stars, and the behavior of gas in its outer disk all hint at the presence of an unseen halo of dark matter that envelops it. Similarly, Andromeda's massive dark matter halo extends far beyond its visible stars, creating a gravitational landscape in which Triangulum is embedded. By studying the velocities of stars, the curvature of spiral arms, and the subtle distortions in gas streams, astronomers can map this invisible scaffolding, revealing the underlying structure that governs motion and interaction across millions of light-years. Despite Andromeda's dominance, Triangulum has maintained its spiral identity. Unlike galaxies that are disrupted by mergers or stripped of stars and gas by tidal forces, Triangulum's disk remains largely coherent and unbroken. This resilience is partly a function of its orbit, which has allowed it to avoid close collisions, and partly a result of its internal structure, which distributes mass evenly enough to resist significant deformation. In this way, the galaxy embodies a quiet persistence, a reminder that cosmic influence does not always result in destruction. Sometimes it shapes, molds, and encourages growth in subtle, enduring ways. The relationship between Triangulum and Andromeda is also a window into the future of the local group. Astronomers predict that in several billion years, Andromeda and the Milky Way will collide, merging into a massive elliptical galaxy. Triangulum's fate during this event is less certain, but simulations suggest that it may orbit Andromeda multiple times before either being absorbed or continuing as a satellite galaxy in the newly merged system. These slow gravitational dances unfold over timescales that dwarf human experience, yet they determine the ultimate arrangement of stars, gas, and dark matter in the local universe. Triangulum, in its modest orbit, participates in this cosmic choreography, a silent witness to the future merger that will redefine the local group. Triangulum's interaction with Andromeda is mirrored on a smaller scale in the galaxy's satellite system. Though it hosts far fewer satellites than its massive neighbor, it is not entirely solitary. Dwarf galaxies in its vicinity, remnants of smaller structures or companions captured long ago, trace paths influenced by both Triangulum and Andromeda. Their presence, distribution, and motion provide insight into the gravitational landscape and history of the local group. Observing these satellites, astronomers can reconstruct the subtle exchanges of matter, the tidal interactions, and the way in which even smaller systems contribute to the complex web of cosmic evolution. Beyond structure and dynamics, the gravitational connection between Triangulum and Andromeda affects star formation. Spiral galaxies respond to tidal forces in predictable ways, compressing gas along certain arms, triggering waves of star formation, and influencing the distribution of molecular clouds. In Triangulum, this may explain the concentration of HI regions in specific locations, where subtle gravitational nudges encourage the collapse of gas and the ignition of young stars. The result is a galaxy that, while calm in appearance, bears the marks of interaction, a visual diary of its gravitational relationship with Andromeda over billions of years. This relationship also provides a lens into the broader mechanics of galaxy evolution. Triangulum serves as a living example of a smaller spiral interacting with a more massive neighbor without losing identity. Many galaxies in the universe are not isolated. They exist in groups, clusters, and filaments where gravitational forces shape their destinies. By studying the dynamics between Triangulum and Andromeda, astronomers gain insight into how galaxies survive, adapt, and evolve in the presence of larger neighbors. It is a delicate balance of influence and resilience, of pull and persistence, illustrated on a scale that challenges imagination, yet reveals universal principles. Triangulum's spiral arms, populated with both young and older stars, offer a record of this gravitational dialogue. The distribution of population 1 stars in the arms may reflect past periods of interaction, with localized clusters tracing the regions where tidal forces compressed gas and sparked formation. Meanwhile, population 2 stars in the disk and halo preserve the memory of more ancient epochs, unaltered by recent interactions. Together, these populations map the temporal layers of the galaxy's history, allowing astronomers to read its evolution like a book written across billions of years. Chemical composition further reveals the impact of Andromeda's influence. Regions of enhanced metallicity in Triangulum's disk may correspond to areas where interactions increased star formation, enriching the surrounding gas with heavier elements produced in successive generations of stars. The outer disk, less affected by tidal forces, retains a more pristine chemical signature, demonstrating the galaxy's balance between internal evolution and external influence. Triangulum, in essence, records the subtle interplay of forces in its stars, gas, and dust, a living testament to its ongoing gravitational relationship with Andromeda. Observationally, Triangulum's connection to Andromeda is evident not only in its structure, but also in its motion through space. Precise measurements of its velocity, rotation, and proper motion allow astronomers to trace its orbit, reconstruct past interactions, and predict future trajectories. These data reveal that Triangulum's dance around Andromeda is both ancient and enduring, a slow-motion ballet unfolding over hundreds of millions of years. Even the faintest distortions in the spiral arms, the wisps of gas extending beyond the disk, are echoes of this cosmic choreography, a reminder that gravity operates subtly yet persistently across vast distances. The relationship between the two galaxies also offers insights into the distribution of dark matter in the local group. Triangulum's orbit and tidal interactions suggest the presence of an extended dark matter halo around both itself and Andromeda, invisible yet governing motion and structure. By studying the effects of these halos on stellar dynamics and gas flows, astronomers gain a clearer picture of the unseen mass that shapes the cosmos. Triangulum, modest in size, becomes a crucial piece in the puzzle, helping map the gravitational architecture of the local universe. Beyond the physical and scientific aspects, there is a poetic dimension to this relationship. Triangulum moves with quiet grace, bound to Andromeda by invisible threads of gravity. Its spiral arms rotate steadily, star-forming regions flare and fade, and halo stars trace ancient paths, all while orbiting a galaxy many times its mass. In this cosmic partnership, we see patience, balance, and resilience, qualities mirrored in the galaxy's serene appearance. It is a reminder that in the universe, influence need not be forceful to be profound, and that subtle, continuous interactions can shape destiny over incomprehensible spans of time. The dance of Triangulum and Andromeda also frames our understanding of galactic ecosystems. Within the local group, galaxies of all sizes interact, exchanging matter, energy, and gravitational influence. Triangulum's role as a satellite spiral highlights how intermediate mass galaxies navigate these environments, maintaining identity while responding to external forces. Its survival, coherence, and ongoing star formation demonstrate the mechanisms that allow galaxies to persist amidst the gravitational complexity of groups and clusters. Ultimately, Triangulum's relationship with Andromeda is a story of balance. It is neither a dominant force nor a passive observer, but an active participant in a gravitational partnership that spans millions of light years. The tidal nudges from Andromeda have shaped its structure, influenced star formation, and guided its orbit. Yet the galaxy retains its spiral identity, its elegance, and its quiet rhythm. In this interplay, we witness the principles that govern cosmic evolution: attraction and response, growth and adaptation, continuity and change. In contemplating Triangulum orbiting Andromeda, we are offered a meditation on cosmic time and scale. Each orbit unfolds over hundreds of millions of years, imperceptible to human perception, yet transformative in the life of the galaxy. Its stars live and die, nebulae glow and fade, and the gravitational bond with Andromeda guides its path through space. The galaxy is alive with process, yet calm in appearance, a luminous spiral moving through the silent corridors of the universe, shaped by forces both subtle and immense. Triangulum teaches us that in the universe, influence is not always loud. Its relationship with Andromeda is defined by steady gravity, slow orbits, and minor distortions that cumulatively guide evolution over eons. Its spiral arms, star-forming regions, halo, and satellites all record the effects of this partnership, creating a living archive of interaction, resilience, and cosmic rhythm. Observing this modest spiral allows us to understand not only its own story, but the broader narrative of galactic ecosystems, a story in which small, intermediate, and giant galaxies interact, evolve, and coexist. In its gentle orbit around Andromeda, Triangulum exemplifies patience and endurance. Its spiral arms remain open and graceful, its star-forming regions flourish, and its halo preserves the memory of ancient epochs. It is a galaxy shaped by proximity, yet not overwhelmed, influenced, yet independent. And in this balance, it offers insight, inspiration, and quiet beauty, a cosmic reminder that even the most subtle interactions can leave lasting imprints, and that the universe's grand patterns often emerge through persistent, gentle forces. Beyond the grand spirals of the Milky Way, Andromeda, and Triangulum lies a quieter yet equally fascinating population, the dwarf galaxies of the local group. Though small and often faint, these diminutive galaxies dominate in number, forming a vast web of stellar systems that orbit, interact with, and shape their larger companions. In their modest scale, dwarf galaxies reveal profound truths about galaxy formation, evolution, and the hidden scaffolding of dark matter that structures the cosmos. Dwarf galaxies are defined primarily by their size and mass. Typically containing between a few million to a few billion stars, they are minute compared to spirals that host hundreds of billions. Their structure varies. Some are irregular, lacking clear form, while others are spheroidal, nearly featureless clouds of ancient stars. Despite this apparent simplicity, each dwarf galaxy carries a story of cosmic history, a record of star formation, chemical enrichment, and interaction with larger galaxies. Among the most well-known members of the local group are the Magellanic Clouds, two irregular dwarf galaxies that orbit the Milky Way. The Large Magellanic Cloud, LMC, is roughly 14,000 light-years across, hosting millions of stars, bright nebulae, and active regions of star formation. The Small Magellanic Cloud, SMC, is smaller but equally dynamic, with rich populations of young and old stars woven through its irregular structure. These galaxies are visible to the naked eye from the southern hemisphere, appearing as faint, diffuse patches of light, a gentle reminder that the universe is layered, with subtle companions often overlooked in the shadow of giants. The Magellanic Clouds are not isolated curiosities. They are active participants in the Milky Way's gravitational environment. Tidal forces from the larger galaxy have drawn out streams of gas known as the Magellanic Stream, stretching hundreds of thousands of light-years through space. This stream is a living record of gravitational interaction, a flowing ribbon of material torn from the clouds as they orbit and sway under the Milky Way's influence. Within these streams, gas can cool and collapse, forming new stars that trace the ongoing dialogue between the dwarfs and their host. In this way, even the smallest galaxies contribute to the cycle of stellar creation, seeding the cosmos with the ingredients of future generations. Beyond the Magellanic Clouds, the local group hosts many other dwarf galaxies, each with its unique character. The Sculptor dwarf galaxy, a spheroidal companion of the Milky Way, is populated primarily by ancient stars, relics from the earliest epochs of galaxy formation. Its stars carry minimal heavy elements, indicating a brief and early period of star formation, followed by quiescence. Nearby, the Draco dwarf galaxy shares a similar story, a compact spheroidal system orbiting slowly, largely untouched by new star formation in recent billions of years. The Fornax dwarf galaxy, in contrast, hosts a mix of stellar populations, including younger stars and several globular clusters, suggesting a more extended history of formation and chemical enrichment. What makes dwarf galaxies particularly important is their role in the hierarchical assembly of larger systems. In the early universe, galaxies grew not as isolated entities, but through the accretion and merger of smaller companions. Dwarf galaxies are the remnants of these building blocks, survivors that never fully merged, or systems that continue to orbit as satellites. Their number, distribution, and motion provide astronomers with a window into the processes that shaped the Milky Way, Andromeda, and Triangulum. By mapping the orbits of dwarfs, we can trace the invisible halo of dark matter that dominates gravitational influence, revealing the unseen architecture of the universe. Despite their modest scale, dwarf galaxies are sites of fascinating astrophysical processes. Some are dominated by dark matter, with mass-to-light ratios far exceeding those of spirals. This means that even though they contain few stars, their motion and stability are governed largely by unseen matter. Others contain bursts of star formation triggered by tidal interactions, or the accretion of gas from their environment. For instance, in the Magellanic Clouds, young stellar nurseries glow brightly, forming massive stars that illuminate surrounding clouds and enrich the interstellar medium. Each star, each cluster, and each diffuse cloud is a piece of a complex narrative of creation, destruction, and evolution on a small scale. The spatial distribution of dwarf galaxies is equally intriguing. Many cluster around their larger hosts, forming a halo of companions that trace the gravitational reach of the parent galaxy. The Milky Way has dozens of known dwarfs in its orbit, while Andromeda hosts an even greater population. Some form planar structures, aligned in surprising coherence, hinting at the effects of past accretion events or shared origins. These alignments challenge simple models of galaxy formation, suggesting that the evolution of satellites is shaped both by internal dynamics and the history of the larger cosmic environment. Dwarf galaxies also provide insights into chemical evolution. Spheroidal dwarfs like Sculptor and Draco are dominated by metal-poor stars, reflecting a history where star formation occurred early and rapidly, with little subsequent enrichment. Irregular dwarfs, such as the Magellanic Clouds, show a wider range of metallicities, indicating ongoing star formation and recycling of material. Studying these differences helps astronomers understand how galaxies grow and evolve over time, and how even small systems can contribute to the chemical complexity of the universe. Interactions among dwarf galaxies themselves, though subtle, are also significant. In some cases, dwarfs may merge with one another, forming larger satellites or triggering bursts of star formation. Streams of stars and gas observed in the outskirts of these galaxies hint at past collisions or tidal stripping, showing that even the smallest systems are dynamic and evolving. These processes mirror, on a reduced scale, the same principles that govern interactions among massive galaxies: gravity, motion, and the transfer of matter and energy. Moreover, dwarfs play a key role in understanding dark matter on small scales. Because they are dominated by this invisible matter, their internal dynamics provide constraints on the distribution and properties of dark matter. Observing how stars move within dwarfs, how tidal forces distort them, and how their gas is retained or stripped, allows astronomers to test theories of cosmic structure formation. In this sense, dwarf galaxies are laboratories for understanding the fundamental physics of the universe, hidden in systems that appear unassuming but are profoundly informative. The combination of large numbers and wide variety makes dwarf galaxies a cornerstone of our understanding of galactic ecology. They outnumber their massive neighbors by orders of magnitude, forming the vast majority of galaxies in the local group. Yet their contribution is not just numerical. They carry the imprint of cosmic history, preserve ancient stellar populations, and interact dynamically with their environment. Without dwarfs, the story of the local group would be incomplete, a narrative missing its quiet, persistent threads. Despite their often faint and diffuse appearance, dwarf galaxies are visually and scientifically captivating. Observations with modern telescopes reveal their stars, clusters, and interstellar gas, showing patterns and structures that are subtle yet rich in information. Their diffuse halos, faint streams, and embedded clusters illuminate the processes of star formation and galactic evolution on a scale that is accessible yet still awe-inspiring. In a sense, dwarfs are the universe's quiet storytellers, preserving the memory of formation and evolution for astronomers to read across light years. In contemplating dwarf galaxies, alongside Triangulum and Andromeda, we see the hierarchy of the local group come into focus. Large spirals dominate the luminous landscape, shaping the gravitational environment. Triangulum, a modest spiral, navigates this environment gracefully, orbiting Andromeda without being destroyed. And dwarf galaxies, numerous and persistent, trace the gravitational contours, preserve ancient stars, and participate in subtle interactions that leave lasting imprints. The local group, therefore, is not just a collection of isolated systems, but a dynamic ecosystem where giants, intermediates, and dwarfs coexist, evolve, and influence one another in intricate ways. Ultimately, dwarf galaxies remind us that cosmic significance is not measured solely by size or brightness. In their small forms lie lessons about survival, evolution, and the interplay of forces that shape galaxies across billions of years. They are laboratories for understanding dark matter, chemical enrichment, and star formation, and they provide the context needed to fully appreciate the larger galaxies they orbit. In the quiet glow of these small systems, we find a profound narrative, the story of a universe built from the modest, the numerous, and the enduring. As we observe these dwarf galaxies, we are invited to consider the scale and depth of cosmic time. The stars within them trace histories that predate much of the structure seen in the Milky Way and Andromeda. Their gas clouds, enriched and shaped by countless generations of stars, continue to foster creation on a small scale, and their orbits, governed by the invisible presence of dark matter, map the gravitational architecture of the local group, connecting every galaxy in a web of subtle forces. In this quiet, unassuming domain, the universe's grand patterns are written in miniature, teaching us patience, observation, and wonder. The local group's dwarf galaxies, from the Magellanic Clouds to Sculptor, Draco, and Fornax, demonstrate that the cosmos is both hierarchical and interconnected. They illustrate how even the smallest members of a galactic system can influence and be influenced by their environment. And they remind us that the universe is a tapestry woven from entities both grand and modest, whose interactions over billions of years create the complex, beautiful cosmos we observe today. In this knowledge, we find both awe and serenity, a quiet reflection on the intricate balance of forces that govern the universe. The local group is more than a collection of galaxies. It is a dynamic, evolving system, a complex gravitational web where giants, intermediates, and dwarfs interact in a slow, silent choreography. Over billions of years, these galaxies have influenced one another, shaped by the unseen presence of dark matter, the flow of gas, and the pull of gravity. In this intricate dance, patterns emerge, histories are written, and the future unfolds in ways both subtle and profound. At the center of this gravitational network are the Milky Way and Andromeda, colossal spirals that dominate the local group's mass. Between them lies Triangulum, a modest spiral whose orbit traces the unseen contours of their combined gravitational pull. Surrounding all three are dozens of dwarf galaxies, from the luminous Magellanic Clouds to faint spheroidals like Draco and Sculptor. Each galaxy, regardless of size, participates in the system's evolution, contributing stars, gas, and motion to the larger narrative. The local group is therefore a living laboratory for understanding how galaxies interact, evolve, and influence one another across millions of light years. The interactions between these galaxies are governed primarily by gravity, a force that operates across vast distances with quiet persistence. Even galaxies that appear isolated are subtly influenced by their neighbors. In Triangulum, for instance, tidal forces from Andromeda have stretched and warped its outer disk over billions of years, sculpting faint streams of stars and gas. In the Milky Way, the Sagittarius dwarf galaxy is currently being torn apart by tidal forces, its stars forming elongated streams that wrap around our galaxy. These interactions are slow and gentle on human timescales, yet over cosmic epochs, they reshape galaxies, redistribute mass, and ignite bursts of star formation. One of the most profound future events in the local group is the predicted collision between the Milky Way and Andromeda. In approximately 4 billion years, these two giants are expected to meet, merging into a single, massive elliptical galaxy. This event, though cataclysmic on a cosmic scale, will not destroy all stars. Vast distances between individual stars prevent direct collisions. Instead, gravity will reshape their orbits, distort spiral arms, and drive gas into intense regions of star formation. Triangulum's role in this future is still uncertain. Simulations suggest it may orbit the merged system several times before either being absorbed or continuing as a satellite galaxy. Its fate, like the intricate interplay of all galaxies in the local group, is written in the language of gravity and dark matter. Dwarf galaxies will play a crucial role in this transformation. Though small, they are numerous, and their motions trace the contours of the local group's gravitational field. Some dwarfs may be accreted by the Milky Way-Andromeda merger, adding their stars to the new galaxy's halo. Others may survive as independent satellites, orbiting the new giant, much as they do now. Streams of stars stripped from these dwarfs will weave into the broader structure, leaving fossil records of past interactions that astronomers can study billions of years later. In this way, even the smallest galaxies influence the grandest cosmic events, their quiet persistence leaving indelible marks on the local group's evolution. Gas dynamics also play a pivotal role. Intergalactic gas, often invisible to the naked eye, flows between galaxies, fueling star formation and feeding central regions. Collisions and tidal interactions can strip gas from dwarfs, sending it spiraling into larger galaxies, where it collapses into new stars. In the Milky Way, the Magellanic Stream is a prime example of such a process. A vast river of gas stripped from the Magellanic Clouds by tidal forces, now slowly accreting onto our galaxy. Similar processes occur in Andromeda and its satellites, demonstrating that interactions are not only structural, but also chemical, redistributing the raw materials of stellar creation across the local group. Dark matter, the invisible scaffolding of the universe, underpins all these processes. Every orbit, every tidal stream, and every galaxy merger is shaped by its gravitational pull. Triangulum, dwarfs, and even the outer halo stars of Andromeda and the Milky Way are bound and guided by dark matter. By mapping the motions of stars and gas, astronomers can infer the shape and extent of dark matter halos, revealing the hidden architecture that governs interactions. The local group is therefore not only a story of visible galaxies, but also of the unseen forces that orchestrate their slow, majestic dance. The local group structure also highlights the balance between isolation and interaction. Some galaxies, like many dwarf spheroidals, exist in relative solitude, evolving slowly over billions of years. Others, like Triangulum or the Magellanic Clouds, are deeply entwined with their larger neighbors, shaped by tidal forces, accretion, and past encounters. This diversity allows astronomers to compare evolutionary paths, understanding how the environment influences growth, chemical enrichment, and star formation. Even in a system as local as our cosmic neighborhood, no galaxy exists truly in isolation. Each is part of a broader, interconnected network. Cosmic timescales transform our perception of these interactions. While human lifespans are measured in decades, the local group operates over millions and billions of years. Spiral arms rotate, halos shift, dwarf galaxies orbit, and mergers unfold, all at a pace that is imperceptible in our short-lived experience. Yet when observed in detail, each subtle distortion, each faint tidal stream, tells a story of motion, interaction, and gradual transformation. Patience and observation reveal the depth and complexity of the local group, a system that appears static to the casual observer, but is alive with change over eons. The narrative of the local group is also a story of creation and destruction. Stars are born in nebulae scattered throughout spiral arms and dwarf galaxies, only to die and return their enriched material to the interstellar medium. Dwarf galaxies are gradually stripped, merged, or disrupted, seeding larger galaxies with stars and gas. Spiral galaxies themselves evolve, their arms winding, their disks thickening, and their halos accumulating the debris of smaller companions. Each process, while subtle on human scales, contributes to the ongoing cycle of galactic evolution, a rhythm that has persisted since the early universe. Interactions in the local group also serve as laboratories for understanding broader cosmological principles. By observing the Milky Way, Andromeda, Triangulum, and their satellites, astronomers can test models of dark matter distribution, star formation efficiency, and galaxy assembly. Streams of stars and gas reveal past mergers and interactions, providing insight into the hierarchical structure formation that shapes the universe at large. Even modest dwarf galaxies contribute critical data, their motions and compositions tracing the influence of gravitational and environmental forces on small scales. The local group, therefore, is a microcosm of cosmic evolution, a system where the principles that govern the universe are observable up close. Beyond the scientific, there is a poetic dimension to these interactions. The local group unfolds like a grand, slow-motion ballet, each galaxy moving in response to unseen forces, each star tracing a path defined by gravity. Triangulum glides around Andromeda, dwarfs orbit, streams of stars arc across halos, and gas flows between systems. There is rhythm, balance, and continuity, a cosmic harmony that persists over billions of years. Even as galaxies collide, merge, or are disrupted, the overall structure of the local group endures, shaped by processes that are both destructive and creative, chaotic and orderly. Looking forward, the local group is poised for continued evolution. The Milky Way-Andromeda merger will redefine the system, yet Triangulum and many dwarf galaxies may survive, continuing their slow orbits around the new structure. Streams of stars, remnants of past interactions, will eventually dissolve into halos, while new stars ignite in the gas redistributed by tidal forces. In this way, the local group demonstrates both permanence and change. Galaxies persist, structures endure, yet the individual components are constantly evolving, exchanging matter, energy, and influence over cosmic time. The local group also teaches us about perspective. While these galaxies may seem distant, faint, or static in our night sky, they are part of a living system, dynamic and interconnected. By observing and modeling their interactions, we glimpse the forces that have shaped the universe, from dark matter halos to tidal streams, from star formation in dwarfs to spiral arm evolution. We learn that even galaxies appearing modest or insignificant play essential roles in the cosmic ecosystem, contributing to the structure, motion, and history of the universe. Ultimately, the local group is a story of continuity, balance, and cosmic rhythm. Its galaxies, from the enormous spirals to the tiniest dwarfs, are bound together in a gravitational network that spans millions of light years. Each orbit, each tidal stream, and each star formation event contributes to an intricate narrative of evolution and interaction. Observing this system is both a scientific and aesthetic experience. We see the underlying mechanics of the cosmos, and we sense the quiet, majestic rhythm that governs it. In contemplating the local group, we are invited to reflect on scale, time, and connection. Galaxies live and die over billions of years, yet their interactions, though subtle, shape the fate of the system as a whole. Dwarfs trace the contours of dark matter, spirals host ongoing star formation, and halos preserve the memory of past encounters. Each component, no matter how small, contributes to the enduring structure, complexity, and beauty of the local group. In this quiet, measured dance of gravity and matter, we find both understanding and wonder, a window into the universe's grand design. The local group reminds us that cosmic evolution is not always violent or abrupt. While dramatic collisions and mergers occur, much of the universe's change is subtle, continuous, and cumulative. Stars ignite in nebulae, gas flows slowly between galaxies, and orbits gradually shift under gravitational influence. These processes, unfolding over incomprehensible timescales, define the rhythms of the universe. The local group is a testament to this slow, persistent evolution, a neighborhood of galaxies where growth, change, and interaction occur with quiet, enduring grace. In the stillness of intergalactic space, the local group continues its intricate dance. Triangulum orbits Andromeda with serene precision. Dwarfs trace arcs through halos, and spirals wind their arms in quiet elegance. Streams of gas and stars mark past encounters, while dark matter shapes the unseen stage upon which all motion unfolds. This is the theater of cosmic evolution, a realm where time stretches, forces operate silently, and the universe reveals its patterns through the subtle interplay of galaxies. And as we observe, we are invited into this rhythm to listen to the quiet pulse of creation and transformation that defines our cosmic home. As we draw this chapter of our journey through the local group to a close, we pause not at the end, but at a quiet interlude in a story that continues to unfold across billions of years. From the majestic spiral arms of Andromeda to the serene disk of Triangulum, and through the quiet persistence of countless dwarf galaxies, we have glimpsed a system in perpetual motion, a network of cosmic interactions, both subtle and profound. Each galaxy carries its own narrative, yet all are connected, bound together by gravity, dark matter, and the silent flow of time. Andromeda, massive and luminous, dominates the local skyline. Its spiral arms stretch wide, luminous nebulae glow with newly formed stars, and its central bulge holds the memory of countless interactions, mergers, and accretion events. Its gravitational influence reaches far beyond its visible edge, shaping the orbits of Triangulum and the numerous dwarf galaxies that weave around it. And yet, despite its size and power, Andromeda is a part of a larger rhythm, an ongoing dance in which each participant, from the smallest dwarf to the mid-sized spirals, contributes to the harmony of the local group. Triangulum, more modest in size but no less remarkable, traces its orbit around Andromeda with quiet elegance. Its spiral arms rotate steadily, dotted with regions of star formation that illuminate the galaxy's disk. NGC 604, one of the brightest star-forming regions in the local group, glows like a beacon, evidence that even smaller galaxies harbor bursts of creativity and energy. Triangulum's resilience, moving under the influence of a far larger neighbor, yet retaining its distinct identity, demonstrates a delicate balance between external influence and internal stability. It is a model of quiet strength, a reminder that survival in the cosmos is often about adaptation, patience, and harmony. Dwarf galaxies, scattered throughout the local group, provide the subtle threads that tie this vast system together. From the Magellanic Clouds near the Milky Way to faint spheroidals like Sculptor, Draco, and Fornax, they trace the gravitational contours of larger neighbors, preserving ancient stars and chronicling epochs long past. Their numbers are staggering, yet individually modest. Many orbit quietly, leaving faint streams of stars in their wake. Some are caught in tidal interactions that strip gas and stars, seeding larger galaxies with the materials for future generations of stars. Even the smallest galaxies play a pivotal role, revealing the underlying architecture of the local group and the invisible hand of dark matter that shapes it. In observing these galaxies together, we see the local group as a dynamic ecosystem. Spirals, intermediates, and dwarfs coexist in a delicate balance, their interactions forming the rhythm of cosmic evolution. Gravity guides their paths, gas flows ignite new stars, and tidal forces subtly sculpt their structures. The local group is not static. It is alive with processes that operate over millions and billions of years, a system in which change is constant, yet often imperceptible to the human eye. Even in their apparent stillness, galaxies are storytellers, narrating the history of formation, growth, and interaction through stars, nebulae, and streams of matter. Time within the local group stretches beyond human comprehension. Spiral arms rotate over hundreds of millions of years, dwarf galaxies complete orbits over billions, and tidal streams evolve gradually, tracing the traces of past interactions. Human eyes perceive only a snapshot, but in that moment, the galaxies are alive with motion and transformation. Each subtle distortion, every glowing nebula, each ancient halo of stars is a chapter in a story that has unfolded for billions of years and will continue long after our own sun has burned out. Looking ahead, the future of the local group is filled with possibilities. The Milky Way and Andromeda are destined to collide in a few billion years, reshaping the system in ways we can model but not fully imagine. Triangulum may orbit the merged entity several times, or perhaps continue as a smaller satellite, while countless dwarfs may be absorbed, disrupted, or remain in quiet orbit. Streams of stars and gas will weave into new halos, preserving the memory of past encounters. The cosmic choreography will continue, unhurried and precise, reminding us that even in the vastness of space, there is a continuity to the dance of galaxies. Yet this is not the end of our exploration. The local group is far richer than what we have observed in this episode. There are faint dwarfs yet to be discovered, streams of stars that trace ancient collisions, and subtle interactions that are only now coming into focus through precise observations and advanced simulations. Each discovery will deepen our understanding of how galaxies grow, interact, and persist, and will reveal the intricate mechanisms that allow a system as complex as the local group to maintain its structure over billions of years. Even now, as we take a moment to reflect, there is beauty in the quiet persistence of these galaxies. Stars are born and die, gas flows and accumulates, and galaxies move in response to invisible forces. Yet the system as a whole remains coherent, balanced, and mesmerizing. In the interplay of creation and transformation, we find both scientific insight and a kind of meditative wonder. The local group is a testament to the elegance of cosmic evolution, demonstrating that change can be subtle and ongoing, yet profoundly shaping the universe. Our journey through the local group has revealed not only the mechanics of galactic evolution, but also the interconnectedness of all components. Spirals, intermediates, and dwarfs are not isolated entities. Their fates are intertwined, influenced by gravitational pulls, tidal interactions, and the unseen architecture of dark matter. The Milky Way, Andromeda, Triangulum, and countless dwarfs form a web of relationships that stretches across millions of light years. Observing this network teaches us patience, perspective, and a deeper appreciation for the scale and harmony of the universe. And yet, even as we conclude this reflection, we remain on the threshold. The local group continues to evolve, its stories far from complete. Future episodes will reveal more: the hidden motions of faint dwarfs, the intricate chemistry of star-forming regions, the whispers of tidal streams, and the long arc of evolution that shapes all galaxies within this local cosmic family. Each discovery, each observation, will add layers of understanding, deepening our connection to this vast and intricate system. In the quiet expanses between these galaxies, there is both solitude and connection. The halos of ancient stars, the streams of gas, the faint glows of dwarfs all testify to processes that operate slowly, yet inexorably. These are reminders that the universe is patient, that evolution unfolds on its own terms, and that each component, no matter how massive or small, contributes to the enduring rhythm of cosmic history. Observing the local group, we are invited to listen to that rhythm, to witness a system that is alive with slow motion, yet harmoniously coordinated. This journey is far from over. There are galaxies yet to be explored, interactions yet to be understood, and mysteries of formation and evolution that still await discovery. As we step back from Andromeda, Triangulum, and the dwarfs we have encountered, we carry with us an understanding of their interconnections, their influence on one another, and the underlying forces that shape them. And as we anticipate the next chapters in this story, we can do so with both awe and patience, knowing that the local group continues its dance quietly, elegantly, and endlessly. In this ongoing exploration, we are reminded that the universe is both vast and intimate. Distances stretch across millions of light years, yet every star, stream, and halo contributes to a single interconnected system. Time stretches across eons, yet the consequences of interactions resonate across the local group. And in this grand measured dance, we find both the power of cosmic forces and the subtlety of their effects. A reminder that the universe's story is one of persistent rhythm, quiet influence, and continuous evolution. As we leave this episode of the local group behind, we carry forward a sense of wonder, patience, and anticipation. There is still more to discover, more galaxies to trace, more interactions to witness. The local group is alive with motion, shaped by gravity, enriched by gas and stars, and guided by the invisible architecture of dark matter. And in every orbit, every tidal stream, every glowing nebula, it whispers the promise of stories yet to unfold. This is not an ending. It is a pause, a quiet reflection, and an invitation to return, to explore deeper, and to continue listening to the rhythm of the cosmos. Thank you for watching Episode 4, Triangulum and the Dwarf Galaxies. Please feel free to leave in the comments ideas for videos you would like to see. Take care and never stop exploring.